Okay, good. Okay, so we have example 1.5. Events A, B, and C have these probabilities. Furthermore, A union C is equal to the empty set. B intersection C is equal to the empty set. And the probability of A and B, written AB, is equal to 1/6. Okay, and so the goal is going to be to find. So for A, we want to find the probability that a probability of A intersection B prime. Okay, so the complement of A intersection B. So that's equal to 1 minus the probability of AB, right? And so it's just equal to 1 minus the given probability for A and B, which is 1/6. So it's 1 minus 1/6, which is 5/6. Okay, and so that is A. If you want to write 5/6 as a decimal, then it would be 0.8333 and so forth. B. The probability of A intersection B prime. Okay, so let's find the probability of A and B prime. And so this is equal to the probability of A minus the probability of AB. Okay, and so let me show you why. So we want the probability of AB prime. We want the probability of AB prime. So let's look at the Venn diagram having sets A and B in it. So we have set A and we have set B, and we want AB prime. So AB prime as a set, let me use purple here. AB prime as a set is the set A intersection B prime, right? That's just the shorthand notation for A intersection B prime, AB prime. So it's the elements that are in A and not in B, or the part of this Venn diagram that's in the set S in the circle A, but not in the circle B. And so this region is in the part in A and not in B. So it's that region. Okay, but you can also think of the purple region as being equal to A minus A and B. So this symbol here is minus. This is subtracting sets. This is a minus sign for sets. It can be the slash to the side like this. Okay, so this is A minus AB. So AB, this thing AB here, that's this thing. Right? So if you take all of A and you subtract that pink region, you get this purple region. Okay. Let me instead of, well, that's fine. But what I'm going to do is I'm going to write it like this. I'm going to put, this is also equal to, I'm going to use the colors in a different way. I'm going to use, this is equal to, let's say you had A, and then you subtracted AB. Okay, so if you look at the Venn diagram for this, you would have the Venn diagram S, you would have the set A, you would have the set B, and then, so this is probably clear already, but A is all of this, right? This is A, but then AB is the red part here, that's AB. So if you take the blue region, which is all of A, and you subtract AB, which is only this, you get AB prime. Okay, so A minus AB is the same as AB prime. Okay, so if A minus AB is AB prime, then since they're equal as sets, that implies that the probability of AB prime is equal to the probability of the same set, or an equal set, And so that's equal to probability of A minus AB, because they're equal sets. But the probability of A minus AB is equal to the probability of A minus the probability of AB. Make sense? Okay, so the probability of AB prime is equal to the probability of A minus the probability of AB. Okay, and so then that's equal to, well, the probability of A was given as 1/2 minus the probability of A and B, which is 1/6. So 1/2 minus 1/6 is 3/6 minus 1/6, which is 2/6, which is 1/3.
Pastor, I have a question regarding the diagram that you drew before. So you see how it says like it was not B. Should we shade the region outside of that's like the outside of A and B? You know, the box or for sample S, because that's not included in B. So we're intersectioning that with A.
Okay, so wait, so I think you said A minus B, right? I did A minus AB, right?
Mm-hmm.
Right. So I make sure I'm understanding you right. I'm subtracting AB, so that's why I'm only shading this part.
No, like you said A intersection B prime. So I'm thinking like, oh, whatever is outside circle B would be like B prime. So
Oh,
shouldn't,
okay, but it's and, right? AB prime is equal to A and B prime. So it's things that are in A, meaning it has to be in the circle A, but it also has to not be in circle B.
so
So,
wouldn't the things outside of A also not be in B? So yeah, that part, should that be shaded or no? Because it's not.
so in order for this point to be in this set, right? It has to not be in B, right? So that's not in B, right?
Yeah.
But it's also has to be in A. But is it in A?
Oh, okay, I got it. Yeah, got it.
Makes
Thank
sense?
you.
If we were talking about A or B, well, if we were talking about A or B prime, it would be included.
Got it. Thank you.
So I think what you're thinking about is the or. Yeah. Okay, but you get it. Good. Okay. Yep. It has to satisfy both conditions. Very good. Okay. Good question. So let's okay, so the next one is the probability of A, B, wait, I already did that. C is the probability of A union B prime. So the probability of A union B prime is equal to 1 minus the probability of A union B. And so that's equal to 1 minus, well, what the probability of A union B is. So by our last theorem, that's the probability of A plus the probability of B minus the probability of AB. Okay, so the probability of A is 1/2 plus the probability of B, which is 1/3, minus the probability of A and B, which is 1/6. Okay, so then you just do 1/2 plus 1/3 minus 1/6. If you think of 6, that's 3/6 plus 2/6 minus 1/6. And so that's equal to 1 minus, and so if you add those, you get 4/6. And so 1 minus 4/6 is 2/6, and that's equal to 1/3. Okay. So that's the probability of A union B prime. Good. Okay, so we found those probabilities. So there's another one. D, we find the probability of A prime and intersection B prime. Okay, so A prime intersection B prime is the same as the set A union B prime. Right, so remember from De Morgan's law, so from De Morgan's law, we have that A prime B prime which is equal to A prime intersection B prime. just shorthand notation for it, is the same as A union B in parentheses prime. That's one of De Morgan's laws, right? Okay, so it's saying that the things that A prime intersection B prime are the thing. If this was set A and this was set B, then the set A prime intersection B prime are the things that are not in A and not in B. So the things that are not in A and not in B is what's outside of both circles. So this region is A prime intersection B prime. But this is also the complement of A union B, right? So A prime intersection B prime is A union B prime. Okay, so we have that. So then we can replace A prime B prime with the equal set A union B in parentheses prime. And so find the probability of A prime B prime is the same, equal to the probability of an equal set, which is A union B prime. And so it's equal to 1 minus the probability of A union B. Okay, so that's equal to 1 minus probability of A union B. And so, we already found this probability. So the probability of A union B prime, we already found, was 1/3. So this is equal to 1. So it's the same as the probability we found in C. Okay, so then in E, we want to find the probability of A union B union C. Okay, so we want to find the probability of A union B union C. Okay, so we have that. Okay, so we have the did I write this right? Oh, okay, sorry. This is A intersection C. It hasn't, this hasn't come up with the problem yet. Okay, so that's A intersection C. Okay, so A intersection C is the intersected. Okay, so so let's look at these two conditions in the problem. A intersection C is the empty set, and B intersection C is the empty set. Okay, so let's go to the whiteboard. So A intersection C is the empty set, and B intersection C is the empty set. These are the two conditions. So this is A, this is B, and this is C. So we're given that A intersection C is equal to the empty set, and B intersection C is equal to the empty set. Okay, these are the two conditions given to us. Good. Okay. Okay. So there's nothing in A intersection C. So there's nothing here. And there's nothing here. This is A intersection C. There's also nothing in B intersection C. So there's nothing here either. And so we want to find the probability of A union B union C. Right. The goal is to find the probability of A union B union C. Now we know the probability of A union B. Okay, because we found it already. Okay, so we know the probability of, so the probability of A union B, we know. Okay, so we're good there. We are given the probability of C. So we have the probability of A union B and we have the probability of C. If these two sets, A union B and C, were mutually exclusive, then we could say that this would be equal to the probability of A union B plus the probability of C. This is if A union B, the set A union B intersected with C is equal to the empty set. Okay, so the set A union B is a set. A union B is a set and C is a set. If their intersection is empty, they're mutually exclusive. When you have two events that are mutually exclusive, then the union of their probabilities the probability of their union is the sum of their respective probabilities. Okay, so A union B as a set is this, right? It's what's in either of those circles, right? So that's A union B. Now C is this set, but the given information tells us that A intersection C and B intersection C is empty. So we know there's nothing here. So if there's nothing in these X'd out regions, then that would mean that the intersection of this red region and blue region is empty, right? Even though the Venn diagram has a spot you could put that it overlaps, there's nothing in that overlapped region. And so that means that this checks out. So this is in fact true. So A union B intersection C is empty. And so that means that the set A union B and the set C are mutually exclusive. And so that means that since this set and this set are mutually exclusive, that means the union of those sets, the probability of A union B union C is equal to probability of A union B plus probability of C. Okay, so because A union B and C are mutually exclusive events, the probability of their union is the sum of their probabilities. And so we use that to get the answer to this problem. So the probability of A union B union C, just to put in between step, is equal to the probability of A union B in parentheses union C, where I think of A union B as one set and C as another set. And this is equal to the probability of A union B plus the probability of C. And this is because A union B and C are mutually exclusive events. And that's because their intersection is empty. A union B in parentheses, intersection C is equal to the empty set. Okay, so then we know the probabilities of A union B and C. The probability of A union B was in the bracket here. It was the 4/6 that I calculated here. It was this. Okay, that was 4/6 or 2/3. So this is equal to 2/3, then plus the probability of C. The probability of C is 1/4. This is 2/3 plus 1/4, and that's equal to 8/12 plus 3/12. Okay, so then that's equal to 11/12. Okay, so that's E. Good. Okay, any questions so far? Okay, so theorem 1.4 is next. If sample space S consists of a finite number, capital N, of sample points, and if each subset with a single sample point is an event with probability 1/n, then for any event capital A in capital S, in capital S, the probability of the event A is equal to n sub A over capital N, where n sub A is equal to the number of sample points in the event A. Okay, so let's look at this theorem. This theorem looks a little complicated, but it's just saying something obvious. Theorem 1.4, if sample space S consists of a finite number of sample points, and if each subset with a single sample point is an event with probability 1/N, then for any event A in S, the probability of A is equal to n sub A over n, where n sub A is equal to the number of sample points in the event A. So what that means is just this. So here's an example to understand the theorem, right? A simple one. If you have a fair 6-sided die, right, then each dice roll has probability 1 over 6, right? There are 6 sides, and so n is 6, right? The sample space consists of 6 sample points, 1, 2, 3, 4, 5, or 6. And so each dice roll has probability 1 over capital N, or 1 over 6, right? So 1 has a probability of 1 over 6 being rolled, 2 is a probability of 1 over 6, 3 is a probability of 1 over 6, 4, 5, and 6, right? All 6 possibilities have a probability of 1 over 6. That's what this says. If each subset with a single sample point is an event with probability 1 over n, then for any event A and S, the probability of A is equal to the number of sample points in that event divided by capital N, the total number of sample points in the sample space. So if I want to know the probability of rolling an even number, there are 3 evens. So the event of rolling an even number would have 3 sample points in it, 2, 4, and 6. And so n sub A would be equal to 3. And n would be the total number of possibilities, which would be 6. So if you have a fair 6-sided die, then each dice roll has probably 1/6. Also, as a further example, if A is the event of rolling an even number, then the probability of the event A is equal to n sub A divided by capital N. And this is equal to, well, there are 3 evens divided by 6, the value of capital N. Okay, and you simplify that to 1/2. But n sub A is the number of sample points in the event A, right? So n sub A here, n sub A is equal to the number of sample points in the event A, which is the event of rolling an even number. Right, and so that means that that's equal to the number of sample points in the event. Well, the event is the even, so that's the set 2, 4, 6. And so the number of sample points in that is equal to 3, right? So that's equal to 3. So n sub A is equal to 3 here, because the event A is rolling an even, and there are 3 sample points in that event. The n sub A is 3, and the total number of rolls is 6, so 3 over 6. And so this theorem is telling you the probability of any event where in the experiment, the probability of any single sample point is 1 over capital N, where capital N is the total number of finitely many sample points in the sample space S of the experiment. Okay, so let's look at a proof of theorem 1.4. Okay, so I'm going to let S1, S2, up to including S sub N sub A be the sample points in capital A. Okay, so if you have your sample points, right? The event A has n sub A number of sample points, right? And so if you were to list those n sub A number of sample points, then you could use subscripts to represent each one. So you could have the first sample point, the second sample point, the third one, up to including the n sub 8 sample point, right? N sub A is the total number. And so the last index, it'll start at 1 and it'll end at the n sub 8th one. So those are the sample points in A. And let E sub I be the event consisting of the single sample point S of I. And that's for I equals 1, 2, ... up to including n sub A. The events E1, E2, up to including E sub n are clearly mutually exclusive. And A is equal to E1 union E2, union E3, union, and so forth, union E sub n sub a. Okay, so for instance, S1 is a single sample point in the event A. E sub 1 would be the event of just single sample point S1. E2 would be the event consisting of the single sample point S2, where S2 is another sample point in the event A. Okay, so each one is reserved for a different S, a different distinct sample point in A. Okay, so the events E1 to E sub n sub A. Okay, the events E1 to E sub n sub A are clearly mutually exclusive because each of them are a different S here in this list. Each of them are a different sample point in the event A. So they're clearly mutually exclusive, and that means that A is equal to the union of them, where each one is disjoint from any other one. Okay, and so since A is represented as a union of mutually exclusive events, therefore the probability of A is equal to the probability of the union of these, because that's what A equals. And those events are mutually exclusive. And so then that equals the sum of their respective probabilities. This is the probability of E1 plus the probability of E2 plus dot 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 plus the probability of E sub n sub A. Okay, and so then that's equal to, well, each of them are a single sample point in the experiment. It's assumed that every sample point has probability 1 over capital N, where capital N is the number of sample points in the experiment. And so what you're doing is you're adding these probabilities, and each of them have probability 1 over N, 1 over capital N. But there are, and so there are n sub a many of them in the sum. Okay. So each of these probabilities has probability 1 over capital N, but there are any n sub a many of them in the sum because we're adding E1 probability V1 plus probability V2 up to including the probability of E sub n sub a. So it's n sub a many of them, and they're each 1 over n. And so if you add n sub a many things where each of them 1 over n, then the sum is equal to n sub capital A divided by capital N. And so what we found is that the probability of A is equal to n sub A over n, and that's what we want to prove. Okay, and so that's the proof. Okay, so we now prove that. Okay, so 1.4.3 is a list of, so I don't want, so we had, so basically we have so far axiom 1, axiom 2, axiom 3, and those were the axioms for a probability set function. We have theorem 1.1, we have theorem 1.2, we have theorem 1.3, and we have theorem 1.4. Okay, so if you want to review this section, those are 7 things to look at. There are other things too, but we have these. Okay, so when you look back at the notes, look at those as a review of what we've done. Okay, as a partial review of what we've done here. Okay, so 1.4.4 is on the assignment of probabilities to key events. Okay, so okay, so we need theorem 1.4 to find the probabilities of complex events. Right? Theorem 1.4 is the one I just wrote down. Okay, so in case that was confusing, this is theorem 1.4. right? The probability n sub a over n, right? So this whole thing with these assumptions. So that was theorem 1.4. So we need theorem 1.4 to find probabilities of complex events. But we can only do that if we have the probabilities of simpler events. Okay, so for instance, right, how do we know the probability of E1 of a single sample point is 1 over n, right? We're assuming here if each subset with a single sample point is an event with probability 1 over n. So we kind of need that assumption in order to use that theorem. Okay, so the solution to needing these things is that we can use subjective probabilities or empirical data. Okay, to have the probabilities of simpler events. Okay, so right, when you roll a 6-sided die, you're assuming that the probability of each side is 1/6, right? In order to say the probability of an even is 3/6. And so you could say that's an example of subjective probability. You could say that, well, I think the number 1 has a 1/6 chance of being rolled, right? I'm looking at the die without someone telling you it's a fair die. You look at it and you say, okay, you know what? I believe that there's a 1/6 chance of a 1 coming up. So you can kind of think of that as the subjective probability, right? And so when someone says, well, what are the odds of rolling even? Well, you say, okay, well, it's 3/6 because I'm making the assumption that the probability of each side is 1/6 because I believe that that's the probability, right? So we have a simpler probability in that case. In life, it would be subjective because we don't know it's a fair die, and it may not be a fair die. And so we may use subjective probability to just make the assumption when we don't know it that the probability of each side is 1/6, right? Or empirical data. So if someone handed you a die with 6 sides and said, what's the probability of rolling an even? You need the assumption that the probability of each side is 1/6. But maybe instead of believing each side is 1/6, maybe instead you say, okay, I want to just believe something. I want to see what the odds of each side is before I assume that that's the probability of that side. So you keep rolling the dice. And so let's say you roll it 6,000 times and you record how many times each number appears. And let's say by some really unlikely case, it probably wouldn't be this exactly. Let's say each number came up 1,000 times. So then you would say, okay, well, I did this experiment of rolling the die 6,000 times. Each of the numbers came up 1,000 times. And so through empirical data, I'm going to say that the probability of each side being rolled is 1/6. And so now you can make that assumption that the probability of each side is 1/6. And from that, you build more complex probabilities using this theorem. And you could say things like the probability of rolling even is 3/6. Okay, so you oftentimes use things like subjective probabilities or empirical probabilities in life or through experiments in science to use that simple theorem in order to calculate probabilities of more complex events. Okay. So as long as the probabilities assigned are consistent with the axioms of probability, all theorems that follow from the axioms may be utilized to solve more complex problems of probability. Okay, so this is the word consistent. So we build our theory of probability by having axioms, right? Set assumptions that were carefully chosen so that they're minimal, but you can deduce from them a lot of mathematics as much as possible, as much as you want that would be relevant and that would make sense. So we have axioms, and then we have the theorems from those axioms. And then we have more theorems deduced from earlier theorems and the axioms, right? So we keep finding out more things from these small set of assumptions, right? So all the things that you conclude from your axioms, as long as your assumptions are consistent with the axioms, the given assumptions of probability, then you can use all the theorems of probability, the correct theorems from them, as you want to calculate more complicated probability problems. But the probabilities that you assign in the beginning have to be consistent with the axioms of probability in order to use the theory of probability. So for instance, if I made a subjective probability and said that I thought the probability of it raining tonight was 2, right? Well, then that would contradict the axioms of probability, right? You can't assign a value of 2, the probability of 2 to something. That would contradict the axioms, right? So if I made the assumption that the probability of it raining was 2, and I wanted to find a complex probability using it, it would fail. I should not use the theory of probability. Okay. So when you assign probabilities, it has to be consistent with the axioms of probability. Okay. You can't assign things anything you want. For instance, if I said the probability of it raining was, I said there's a 50% chance it's going to rain and a 40% chance it's not going to rain, then that would also contradict the theorems of the axioms of probability. Right, so that there can't be a problem with the probabilities I assign. Okay, but as long as there's no problem with them, then you can use the entire theory of probability from those assumed probabilities, right, to find more complicated ones. Okay, here's another example. So this is example 1.7. So example 1.7 says about Helen feels her odds against getting an A in biology are 1 to 3. And the odds against getting an A in calculus are 1 to 4. She feels the odds against getting an A, against getting A's in both courses are 2 to 3. Assuming she is right, what is the probability? So assuming she is right, what is A, the probability of Helen will get at least one A? Okay, so let's start here. So I had just to write this all down. So let's look at this again. So example 1.7. Helen feels her odds against getting an A in biology are 1 to 3. And the odds against getting an A in calculus are 1 to 4. She feels the odds against getting A's in both courses are 2 to 3. Okay, so we're assuming all those things. We're going to find this probability of her getting at least one A. So first, let's figure out each of these odds. So she feels her odds against getting an A in biology are 1 to 3. This is the first thing that's said here. Odds against. Odds against means the probability of something not happening. Okay, so getting an A in biology. So odds against getting an A in biology, meaning what's the probability that she does not get an A in biology? Okay, so when it says that green part that I highlighted is going to correspond with this thing I'm going to write here. So that corresponds with the probability just green. Okay, there we go. Good. Her odds against getting A in biology. So the probability of A prime, where A is the event of her getting an A in biology. So I'm going to write that. Okay, so event A is the event of getting an A in biology. Okay, so the green, her odds against getting A in biology. So the probability of not getting A in biology is equal to not 1/3, but 1/4. And because it's 1 over 1 plus 3. That's how odds work. So if the odds of something are 1 to 3, right? Then that means it's 1 over 1 plus 3. And so I'm going to go to the whiteboard to explain this. Okay. So if the odds of something happening, the odds of some event. So if the odds are 1 to 3. So I'm doing this in steps. So we're really finding the odds against something happening, but just the odds of something. The odds are, let's say the odds are 1, 2, 3. I'm going to use marbles to depict this. Okay. So if you're looking at something happening, saying the odds are 1 to 3, then I'm gonna be talking in green because that's. But let's say it's 1, 2, 3. Okay. Well, then that means that if something were to happen, this event that you're talking about, this 1, right? Let's say it happened once, right? And then let's say it didn't happen 3 times. That would be kind of a visualization of what 1 to 3 means. Every time this thing that you're looking at happens once, correspondingly, it could not happen 3 times. Okay. So if you would try this 4 times, 3 times it would happen, 1 time it would happen, and 3 times it wouldn't. So saying the odds are 1 to 3 means every time you see something happening once, you would see it not happening 3 times. And so the probability of it would be 1 over 4, because not because there are 4 times, but the ratio is 1 to 4, right? 1 out of every 4. So in order to see this thing happening, since there's a 1 to 3 correspondence between happening and not happening, then the probability would be every time you see this once, you see 3 not. And so the probability of odds 1 to 3 would be 1 over 1 plus 3, which is 1/4. Make sense? So 1 to 3 odds means 1/4 probability. But it's not, that's one piece of this puzzle. So it says the odds against an A in biology 1 to 3. So the event is not getting an A. The event is not getting an A. But still, the odds are 1 to 3 for not getting an A in biology. So I want to call this B. Sorry. Getting an A in biology, I want to call B. So B prime is going to be not getting an A in biology. Okay, so the probability of not getting an A in biology is 1 over 1 plus 3, because the odds against her getting an A in biology is 1 to 3. So that's equal to 1/4. Okay, so the probability of not getting an A in biology are 1/4. It's 1. The probability of not getting in biology is 1/4. Okay, so now let's look at the odds. It says the odds against getting an A in calculus are 1 to 4. So let's use not that blue. So now the odds against getting an A in calculus are 1 to 4. And so we need a name of another event. Well, since we're talking about calculus, then I'm going to make C the name of this event. So C is going to be equal to the event of getting an A in calculus. Okay, so we keep talking about the grade A. And so we're going to use the letters to denote the names of the classes. Let's looking at C, the letters are from the names of the classes. So C is the event of getting an A in calculus. So the odds against getting an A in calculus. So the odds against, so that means you don't get an A. So what we want is C prime, the probability of not getting an A in calculus, the probability of C prime. And so then that's equal to, I could have chosen C to equal the event of not getting an A, but if I then said the probability of C was the probability of not getting an A, it would be, I think, more confusing. So I let C be the event of getting an A, even though it's indirect to here, and C prime be what it's given. So what's given to us by my choice of notation is the probability of C prime. Okay, so the odds against getting an A in calculus are 1 to 4. Well, if the odds are 1 to 4 of the event C prime happening, then that's equal to 1 divided by 1 plus 4. Right? Because that's how the odds work. And then that's equal to 1/5. So the probability of C prime is 1/5. And so I'll illustrate that also. So if you have, it's 1 to 4, the odds are 1 to 4, right? Odds are 1 to 4. So if the odds are 1 to 4, then for every one thing you have it happening, that would be this one, then for every 4 it doesn't. Just gonna shade in because I shaded the other ones. So the odds are 1 to 4 means the probability of that event would be 1 over, right? The probability of this event, which have odds 1 to 4, would be equal to 1 divided by the total. Well, 1 divided by 5, because for every time it happens once, the ratio is 1. For every 1, there's 4 where it doesn't, so that's 1/5. Okay, so you see how the odds still work that way. So that means probability C prime is equal to 1 over 1 plus 4, which is 1/5. Okay, so she feels the odds against getting A's in both courses are 2 to 3. So we don't need to do notation. But we just need to talk about a particular set. So she feels the odds against getting A's in both courses are 2/3. So let's use another color. Let's use purple. And so this probability, what this is saying is that the probability of saying that the probability of this event, A's in both, against getting an A's in both courses, means she does not get an A in both. So getting an A in both would be BC, okay, because that would be an A in biology and an A in calculus. But against getting an A in both courses means the complement of that event. So it would be B and C prime, B and C in parentheses and then prime. And so the probability of not getting an A in both courses is, the odds are 2 to 3. And so that means the probability is 2 divided by 2 plus 3. So the probability is 2/5. Okay. So since the odds against are 2 to 3, then that means the probability is 2 divided by 2 plus 3, which is 2/5. Okay, so we have the assumption of these 3 probabilities. Assuming she is right, what is the probability that Helen will get at least 1A? Well, getting at least 1A would mean getting an A in biology or in calculus. So the probability of getting at least 1A would be B, probability of the event B union C, A and 1. At least 1 would be one or the other. It's true. When it's one or the other, that includes the possibility of getting an A in both. Okay, so what's the probability of B union C? Well, that's equal to 1 minus the probability of the complement of AB. The set, I mean, not BC. So the complement of B and C. Oh, no, wait. Sorry, that's the complement of B prime and C prime. Okay, I could do that. Okay, so this is equal to the probability of B plus the probability of C minus the probability of BC. Okay, so then we ask, what is so this is equal to the probability of B. Well, if the probability of B prime is 1/4, then that means this is equal to 3/4, right? We have the probability of B prime is 1/4, so the probability of B is 3/4, plus the probability of C prime is 1/5, so the probability of C is 4/5, and then minus the probability of B and C. But the probability of B and C prime is 2/5, so this is 3/5. And so then that's equal to, so now you just calculate this. So 20ths would be the common denominator. So this is 15 20ths plus 16 20ths minus 12 20ths. And so if you add those up, you get 19/20. And 19/20 as a decimal is 0.95. Okay, because 1/20 is 0.05. And so 19/20 is 1/20 less than 1. And so you just take 0.05 away from 1 and you get 0.95. Okay, so that's A. So B, so we're asking what is the probability of each of these things? So what is the probability of no A's? That's the next question. Probability of no A's. So B is the event of an A in biology, C is the event of calculus. So the probability of no A's is the same as the probability of not B and not C. Right, not getting an A in biology and not getting an A in calculus. Well, so this is equal to the probability of the complement of B union C. B union C. It's a complement of that set. Okay, so yeah, I mean, you can write this notation and it's going to be equal to that. We already said this is the same as at least B union C. Probably B union C is the probability of Helen will get at least one A, right? So this is the same as equal to the probability. I guess I'll continue on this track and I'll just write this a second. This is minus the probability of B union C. This is equal to 1 minus the probability we just found, which is 0.95. That's equal to 0.05. Okay. Another way to think of it using words is that the probability of no A's is equal to 1 minus the probability of at least one A, which is what we found in the last example. Probability of at least one A was 0.95. So this is equal to 1 minus 0.95, which is equal to 0.05. Okay, so that's using more words. So either way, you get the answer is 0.05 for the probability of no A's. Okay, C, what is the probability that Helen gets only one A? So exactly one. So if she gets only one A, that means that she only gets an A in biology or only gets an A in calculus. Okay. Well, one way to do it is it's equal to the probability of an A in both courses minus the probability of probability of at least one A. Probably at least one A minus the probability of an A in both courses. Okay, so right, if she gets only one A, then that would mean she gets at least one A and not an A in both. That would mean that she would get exactly one or the other. So the probability of at least one A we already found in part A, that was 0.95. But then you subtract the probability of an A in both courses. Well, the probability of her not getting an A in both courses is 2/5. So that's 3/5. Right? 3/5 as a decimal is 0.60. So let me just put this as a note. Note the probability of an A in both courses is equal to the probability of BC, right? Well, that's equal to 1 minus the probability of the complement of BC prime. And that's equal to 1 minus, well, we have probability BC prime was 2/5. This is 1 minus 2/5, which is 3/5. So the probability of A in both courses is 3/5, and 3/5 as a decimal is 0.60. So the probability of A in both courses is 0.60, and so we substitute the probability of A in both courses with 0.60. So that's equal to 0.95 minus 0.60, which is 0.35. That's the answer. Okay, so probably Helen gets only one A. Okay, any questions? Okay, so next is 1.4.5. That's the probabilities of 0 and 1. Okay. If A and B are events, despite your intuition, the probability of A equaling 1 does not imply an event A is certain to happen. And the probability of B equaling to 0 does not imply that an event B cannot happen. Okay, and so here's an example illustrating that. Okay, so example. Here's a cold example. Suppose you choose a number X at random between 0 and 1 inclusive. Okay, so in this example, you choose a number X at random between 0 and 1 inclusive. 0 and 1 inclusive means that you're considering 0, 1. It could be 0, 1 also. Okay, now finite closed interval 0, 1. Okay, so let's say you wanted to think about the probability of 1/4 is less than or equal to X less than or equal to 3/4. Well, that should, you probably have some intuition on this. That would be 1/2, right? Because if you think of the space that's taken up by the interval 1/4 to 3/4 and the space of the entire unit interval, it takes up half the space. So if you look at the unit interval, and so here's 0 and here's 1, and you're looking at from 1/4 to 3/4. Well, what is the ratio of that part that's taken up by from 1/4 to 3/4 in the entire region? Well, the probability of 1/4 less than or equal to X less than or equal to 3/4 in the interval from 0 to 1 inclusive, well, then that would be equal to, well, 1/2 is the length of this green region, right? So I'm going to use green for that. So then, so this would be 3/4 minus 1/4. That's how you would calculate the length, right? The length of this is 1/2. 3/4 minus 1/4 difference. But then you're dividing it by the entire length of the space. The entire length of the space is 1. So it'd be 3/4 minus 1/4 minus over 1 minus 0. And so what you would get is that the amount of space taken up on that where X could lie in is 1/2, but that's out of the length 1. So 1/2 divided by 1 is 1/2. So probably the X is between 1/4 and 3/4 inclusive is 1/2. It takes up half the total space in the unit interval, right? Okay, so that makes sense intuitively, right? So the probability of that is 1/2. So if you choose a number at random, the probability that it's between 1/4 and 3/4 inclusive, if you can only choose in the unit interval, is 1/2. Now, if you take the probability of 1/8 less or equal to X less or equal to 3/8 less or equal to X less or equal to 5/8, then that's equal to, well, 3/8 to 5/8, that's 2/8. So that's 2/8 of the entire interval. And so that's 1/4. Okay. And so this interval has length 1/4 out of the entire interval, which is length 1. Okay. So if we were looking at an x at random between 0 and 2, then even though this is length 1/4, it would be 1/4 over 2. And so you'd have 1/8. This is probability, right? But it's because we're choosing only in the unit interval. That means you're dividing these lengths by 1. And so these probabilities are the same as the length here, but for the situation we're in. Okay, so then the next, so that's the probability of that. And if you wanted to know the probability of 7/16 less or equal to x less or equal to 9/16, well, that's equal to 1/8, because the interval from 7/16 to 9/16 is 2/16 in length. That's 1/8 divided by 1, which is 1/8. Okay, so you have these shrinking intervals, and so the probability of x lying somewhere in these smaller intervals, they're getting smaller: 1/2, 1/4, 1/8, and you can keep doing this, and you can keep following this pattern where you shrink the intervals that it's in, and the lengths are half each time. So originally you have the unit interval. So I'm just gonna, okay, so you have the unit interval. It's going from 0 to 1. This is 1/2. This is 1/4. So we start with 1/4. This is 1/2. And this is 3/4. Okay. Now, okay, so this interval is 1/2 in length. Good. Okay, so now next, you have 3/8 to 5/8. Okay, so now you have this interval, and then the next one, because this point is this is the 1/2 mark point here. Okay, and so then the next subinterval would be 7/16 to 9/16. Okay, so every time we have intervals being halved, we have the first interval from here to here. Oh, it's not. Oh, no, it's closed. So we have the first closed interval from here to here where we could choose from. Then next we have from here to here. And then the next one is from here to here. We'll keep going. Right, and so they get smaller and smaller, and they're half in length each time. And so this pattern continues, and we keep getting we keep halving the length of each of these intervals. And they keep getting smaller and smaller, and see that they're centered at 1/2. Okay, so that's the situation that we're in. Okay, so if you continue in this way, so if you continue in this way and you were going to ask yourself, what is the probability that x is equal to 1/2? Okay. Well, what would the answer be? Well, it can't be negative, right? Because we're only in between 0 and 1. Also notice that x equals 1/2 is in all of these subintervals, right? 1/4 to 3/4, 3/8 to 5/8, 7/16 to 9/16. So 1/2 is always in the very center. But by the way we're choosing our intervals, we're choosing it appropriately so that x equals 1/2 is always in every subinterval. And every subinterval is always half the length of the previous one. So they're all being half in length. And x equals 1/2 is right inside the intersection of all these. It's in all of them. And so the probabilities are half each time. So we start with a half, then a fourth, then an eighth. The next one will be a 16th, then 1/32. But x equals 1/2 is in all of them, which means that this probability has to be at most, but probably less than, but at most, each of these probabilities. It has to be at most 1/2, and at most 1/4, and at most 1/8, and so forth. But if it's at most all of them and all of these are always halved, then the probability of x equals 1/2 cannot be positive. Okay, no matter what probability, if we assume this was any positive probability, I could just follow this process, which is repeated infinitely, until I have 1 over such a large number that this probability would be smaller than the one I assigned to the probability of x equals 1/2. And so then that would contradict whatever positive probability I assigned to it. So the probability of x equals 1/2 is 0. Okay, it has to be 0 because if we assigned any positive probability to the event x equals 1/2, it would be larger than the probability of some interval containing x equals 1/2. Okay, so no matter how small this probability is, that assigned positive probability would end up eventually being larger than the probability of some very, very small interval containing that number. And any set that contains a number has to have at least as large a probability. You can't have a bigger set have a smaller probability than the probability of something entirely contained in it, right? The bigger the set, the more the probability has to be, or the same, right? You can't increase the set and suddenly the probability goes down. And so the probability of x equals 1/2 has to be at most all those. And so since it can't be positive, it can't be negative. That contradicts the axioms of probability. It can't be positive, it already can't be negative. That means it has to be 0. That would lead to a contradiction. So the probability, because okay, so any positive probability leads to a contradiction, and it already can't be negative because of the axiom, right? And so it has to be 0. So the probability of x equals 1/2 equals 0. But the example was, suppose you choose a number x at random between 0 and 1 inclusive. And so if you're choosing a number at random from 0 to 1 inclusive, then you could choose any number, right? And so you could choose number 1/2. So even though we know you can choose the number 1/2, we also know that the probability of it in this example is 0. And there's nothing wrong with that. It's just there's so many numbers between 0 and 1 inclusive that it's not that you can't choose. When you find the probability of something is 0, it's not that it can't happen. It's just almost surely won't happen. Okay? It's just the chances of it happening are astronomically, ridiculously small. Okay? We're not saying a human being chooses a number at random. We're saying that, like, if a computer chose it and we asked it to choose a number at random between 0 and 1 inclusive, right, and being completely impartial with all the numbers, that you could live your entire life and this thing could be running on repeat your entire life, you will never see it. You would probably not see it choose 1/2, right? It could, but it'd be really, really, it'd be so ridiculously unlikely that saying it's not going to happen would be a perfectly reasonable thing to say. Okay, so the probability we see here that the probability of something happening being 0 does not mean it can't happen. This is an example of it. Okay, and since we already did this, we could then get the opposite very easily, right? Since the probability of x equaling 1/2 is equal to 0, we also know that the probability of x not equaling to 0 is equal to, of x not equaling to 1/2 is equal to 1, right? So we also know that now the complement of this, the probability of it has to be 1 minus this, or 1, right? 1 minus 0, which is 1. So the probability of x not equal to 1/2 is 1. Now, you used to think that the probability of something happening is 1, that means it would definitely happen. But just as before, we could choose number 1/2, which means that if we chose 1/2, that would mean that x not equaling 1/2 did not happen. Wait, if we chose 1/2, then it did not happen that x does not equal 1/2. It's a double negative, right? So if we chose 1/2, that would mean it would be false to say that we didn't choose 1/2, because we did. So that would be an example of how saying the probability event is 1, but it still happens anyway. Okay, but if we choose x equals 1/2, that would mean that it is false to say that x does not equal 1/2. It's not true that x does not equal 1/2. It does. Okay, so but we can choose 1/2, and so that's an example of saying probably an event is 1, but it doesn't happen. Okay, so our conclusion, which I said, we're just writing words. Conclusion is if probability of an event C is 1, then event C is almost sure to occur. Okay, so we have to relax our conclusion from what intuitively we thought it was. We can't say it does happen. We say it's almost sure to occur. So if the probability of an event is 1, then event C is almost sure to occur. Okay, so the meaning of almost sure is complicated and requires advanced mathematics. Okay, and requires a lot more mathematical sophistication to understand. Okay, and we cannot say C is sure to occur. Okay, so we cannot say C is sure to occur just from knowing its probability is 1. Okay, okay, to learn more about almost sure events or the mathematics behind such a concept, you should study real analysis. Okay, real analysis slash measure theory. It's really measure theory, which sits inside of real analysis. Okay, so measure theory deals with measures of sets and deals with measures of zero sets, and so it has to do with that. Okay. Okay, so good. So we're done with that. Okay. Let me assign homework. Maybe let's see. I think this is a good time. So I already assigned homework 1, right? Okay, so let's. No, yeah, sorry. Okay, so let's go back here. Oh, wrong one. Okay, I'm sorry, not yet. Okay, so let's talk about chapter 2. Okay, so chapter 2. Oh, we'll stop here. Okay, it's 7:47. I should stop. Okay, so this is a good place to stop. We just finished chapter 1. Okay, so just finished chapter 1. Okay, so next class we will start chapter 2. Right. The next homework, when it's not, I'm not assigning it yet. The next homework, I just put it up twice here. That's all right. So next homework has 1.4.5 in it. You can start it if you want, but it also has 2.2, and so I'm not assigning it yet. Okay, so there's no homework right now being assigned. If you want to start homework 2, though, you can. Okay, and so this is from 6:30 to 7:45. So we'll stop there. Okay, I'm going to stop recording. So I figure